Bien, bonjour à toutes et à tous. Donc, on est en train de débuter la partie non publique de ces 5e conférences Jean Piaget. Pour ceux d'entre vous qui n'étaient pas hier à la conférence publique, je pense que vous avez les différents éléments. Je n'ose pas imaginer ce qui se trame derrière. Et donc, en tout cas, tous les renseignements peuvent être donnés à l'accueil, comme vous le savez. Et puis, on se retrouvera au moment du déjeuner pour partager le déjeuner. Now I switch to English to have the pleasure to introduce our keynote speaker. So it's a great pleasure to welcome you to today's keynote with Professor Andrew Shtulman, who is a leading scholar in cognitive developmental psychology and professor at Occidental College. Dr. Shtulman earned his BA from Princeton and his PhD from Harvard, and since 2007 he has led groundbreaking research at Occidental College, most notably through the Thinking Lab, which investigates how people acquire, represent, and use the tens of thousands of concepts that adults hold. His work has been recognized with an NSF Early Career Development Award, a James McDonald Scholar Award, and his findings have appeared in top journals such as Cognition, Psychological Science, and Child Development. He also served as president of the Society for Philosophy and Psychology. Prof. Shtulman is the author of 2 highly influential books. His 2017 work, Science Blind, Why Our Intuitive Theories About the World Are So Often Wrong, explores why deeply rooted childhood intuitions, such as the belief that heavier objects fall faster, persist even after years of science education. His latest book, Learning to Imagine, The Science of Discovering New Possibility, in 2023, focuses on our capacity for creativity, demonstrating how imagination evolves and can be intentionally cultivated. Both books come highly recommended. At the Thinking Lab, Professor Shtulman and his team conduct experiments that reveal the coexistence and often the conflict between intuitive and scientific reasoning. Their work spans domains such as evolution, physics, mathematics, and children's belief in supernatural phenomena. Beyond academia, Dr. Shtulman's research has reached a broad audience, having been featured in Scientific American, The New Yorker, and on CBS News. He's also sparked wide interest through podcasts, including Michael Shermer's Science Salon and Unsiloed podcast. Today, he will guide us into the fascinating terrain of cognitive reflection, which is our disposition to override intuitive responses in favor of analytical reasoning. So please join me in giving a warm welcome to Andrew Shtulman.
Thank you for inviting me. I want to start off with an apology for not speaking on the main theme of the conference, analogy, but I will be hitting on all the sub-themes, development, education, and learning. And the skill that I'm going to be focused on, cognitive reflection, I think probably does play a role in analogy. I just haven't studied that directly, but maybe that's something we can talk about in the Q&A. All right, so I wanted to begin with a pop quiz. Great way to start your morning. Imagine there's this lake, and in the lake there's a patch of lily pads. Every day the patch doubles in size. If it takes 48 days for the patch to cover the entire lake, how long would it take the patch to cover half of the lake? So most people give the answer of 24 days. They take 48 and divide by 2. But I'm sure none of you thought that right. The correct answer is 47 because the lily pads are growing at an exponential rate. So it was just 1 day prior to the lake being covered that the lake was half covered, given that stipulated rate of growth. So the lily pad problem is designed to elicit an erroneous intuition that you can stop and think about and realize is wrong and generate a more analytic response in its place. It's one of 3 problems that was originally developed to measure this phenomenon of cognitive reflection. reflecting on your own cognition or thinking about your own thinking. And reflection is probably not a unitary competence. It probably involves several sub-skills. It would involve error monitoring, so asking yourself, does 24 actually answer the problem posed? It involves inhibition. Should I respond with 24? Because that's presumably the answer that pops into most people's head. If you do decide to not respond with 24, you have to engage some cognitive flexibility and think about what other approaches there are to answering this problem. And then it also requires a degree of analysis to actually answer the problem correctly. So the lily pad problem is one of 3 problems introduced by Shane Frederick in 2005 as part of the cognitive reflection test, or CRT. They are 3 brain teasers that all elicit an intuitive response that can be flagged as wrong and overridden with some reflection. And you might have seen these problems in other places. The reason why I, as a cognitive developmental psychologist, became interested in the CRT is because it ends up being a very powerful predictor of a lot of higher order cognitive skills. So adults' CRT scores predict normative decision making, that is, making decisions without the influence of problematic heuristics and biases. It correlates with normative thinking dispositions like the need for cognition and actively open-minded thinking. It correlates with your understanding of complicated science concepts, with your acceptance of controversial scientific claims. It correlates with the rejection of paranormal ideas, your ability to learn patterns of causation from covariation data, your ability to detect fake news, your ability to cooperate successfully with others, the avoidance of stereotyping, and many more. At this point, there are thousands of studies that have involved the CRT, and it seems to predict everything. But one problem with the adult CRT literature is that it doesn't say where where cognitive reflection comes from. Cognitive reflection is treated as a skill or a disposition, it's used as an individual difference variable to separate adults. Some people seem to be high on it, some people seem to be low on it, but has that always been the case? Or is there a different way of thinking about cognitive reflection as a skill or an ability that develops across the lifespan? So, with that focus in mind, there's at least 3 reasons why developmental psychologists should be interested in cognitive reflection. So the first is methodological. Cognitive reflection is very easy to administer. It's just a collection of brain teasers. The first test was 3 items. There are many versions now, but they all take just minutes to administer and to complete. And they predict lots of different forms of rational thought and behavior. Theoretically, cognitive reflection tests provide a window onto the domain general prerequisites for domain-specific cognition. Because brain teasers tap into some general processing abilities that seem to be involved in many specific tasks. And then there's educational reasons to study cognitive reflection, because people who are cognitively reflective are less prone to errors. They are they are ready to learn. And so if we can promote reflection in individuals, presumably we can improve learning outcomes. So I will be talking today about the CRT-D. D stands for developmental. So it's a cognitive reflection test that is designed for children, elementary school age children. It's a test I developed with a former postdoc, Andrew Young. And the research I'll be talking about in the presentation has been all published in these various papers. You can find them on my CV, my website. All right, so I want to convince you of 3 main claims today. The first is that children's cognitive reflection can in fact be measured, and that it is predictive of the same sorts of things that adults' cognitive reflection is predictive of, rational thought. And that's true even if you control for children's age and cultural background. I also want to show you some evidence that cognitive reflection predicts not just performance on heuristics and biases tasks, but also reasoning about domain-specific topics. And I'll focus on science. And then finally, I'll turn to some attempts to improve cognitive reflection, and we found that encouraging children to consider the adequacy of their intuitive responses can in fact lead to higher cognitive reflection scores. So starting with measuring children's cognitive reflection and validating it, so we knew that to create a developmental version of the CRT, we needed brain teasers, and that's the structure of these items. But they had to be brain teasers that a child between kindergarten and 6th grade could answer, where they could correct their intuitive response with reflection. So that meant we couldn't require math. The original CRT, all 3 problems had math on them, and kindergartners don't know much math. They had to draw on general semantic knowledge instead, and also early developing knowledge if we were expecting to give it to young children. And they also had to be the kind of problems that triggered a single self-evident response, as opposed to just being difficult problems that triggered no response at all. So I'll give you some, so we scoured the internet for brain teasers that already are out there for use with children, as well as existing adult cognitive reflection tests that were verbal in nature and had some items on them that could be adapted for use with children. So here's some of the items that we chose. What do cows drink? So because of the association between cows and milk, they produce milk. The first answer that pops into many people's heads is milk. But they don't drink the milk they produce, they drink water. Or how about if you're running a race and you pass the person in 2nd place, what place are you in? So the answer that pops into many people's heads is 1st, but you haven't passed the person in 1st place, only the person in 2nd place, so you're now in 2nd. All right, so these 9 items comprise the final CRTD after lots of pilot testing. And next to each of the items is the percent of children who answered that question correctly, followed by the percent of children who provided the incorrect lure response, followed by the percent who provided some other random response. So the response structure we were looking for was that children would provide the lure response most often, next most often they provide the correct response, and least often they provide just random other responses. And in general, that was true for these 9 items. It's important to recognize that what makes a brain teaser is that there's an intuitive response that's elicited, as opposed to just confusion or a whole range of random responses. So next, we wanted to validate the CRTD by showing that it predicts the same things that the adult CRT predicts. And the adult CRT was always designed to be a test of your ability or your predisposition to privilege analysis over intuition. And there's a whole series of tasks in the cognitive psychology literature that have that structure. They're heuristics and biases tasks. So we wanted to show that performance on the CRTD tracks performance on heuristics and biases tasks, and also endorsement of normative thinking dispositions, like the best ways of thinking. Do children agree that those are good styles of thinking? So we actually, in addition to creating a child-friendly version of the cognitive reflection test, we also had to create some child-friendly versions of heuristics and biases tasks, because in many cases, those didn't exist either. So our participants in our first study were 96 children between 5 and 12. All the children that I'll be telling you about today were recruited from public playgrounds in the Los Angeles area and tested on-site with iPads. We also recruited a group of adults through Amazon Mechanical Turk, and we administered them we gave them the same tasks along with the original CRT and an alternative version of the CRT to see whether or not the CRTD can be used across the lifespan or only is applicable to children. To measure rational thinking, specifically we measured denominator neglect. A sample problem in this task is that children are asked to decide between two games, a game where they have a 9 in 100 chance of winning, or a game where they have 1 in 10 chances of winning. And the rational choice should be 1 out of 10. That's a slightly better chance of winning than 9 out of 100. But many children go with 9 out of 100 because there's 9 chances there and only 1 chance for the other game. We measured belief bias syllogisms, the performance on this task, where we gave children valid syllogisms with unbelievable conclusions, like all pigs fly, Wilbur is a pig, therefore Wilbur flies. And the question was, do they agree that that conclusion is true given the premises? And then we also gave them the opposite, invalid arguments with believable conclusions. We measured base rate sensitivity, where we asked them whether or not they accept a claim based on evidence or a contradictory claim based on an anecdote. Like you go to an amusement park and there's 2 roller coasters, A and B. Most park attendees in a survey preferred A, but your friend prefers B. Which one do you prefer? And then other side thinking, where children took a stance on an issue, and then we asked them to generate reasons in favor of that stance as well as against that stance. So the specific issue was, should children have cell phones? They all said yes, but not all children could then generate reasons why that was a bad idea. Normative thinking dispositions we measured too. Need for cognition. We used a child-friendly version of the scale with items like thinking is fun for me and I like learning new things. And actively open-minded thinking was another disposition we measured with items like it is good to listen to the other side of an argument and changing your mind is a bad thing. That item would be reverse coded. Because to be open-minded, you should change your mind. So first, let's just look at average scores on the CRTD as a function of age. So the size of the circles in this diagram indicate the percent of participants of that age who got that number of items correct. And the red diamonds indicate average responses, average scores. So you can see that as children are getting older, their scores are increasing. Also, scores on this test were not at floor or at ceiling. There's plenty of variation, which might then track variation in other tasks. And this finding by itself is interesting, that we're showing that cognitive reflection is changing with age, because when you just look at it with adults, you have no idea whether it develops at all. It's all or nothing kind of ability when used as an individual difference measure. All right, so children's scores on the CRTD did correlate with their scores on our measures of rational thought, almost all of them, and they correlated very strongly with the composite measure. And then children's CRTD scores also correlated with their endorsement of normative thinking dispositions, including a composite measure. We ran some regression analyses to determine whether CRTD uniquely predicts rational thought and normative thinking dispositions by controlling for age. So we found that age did in fact predict both of those measures, but even when we control for age, cognitive reflection scores continued to predict rational thought and endorsement of normative thinking dispositions. Turning now to the adults, we found that adults' CRTD scores correlated with their scores on the original CRT as well as alternative adult versions of the CRT. So adults tended to score quite high rather than between 0 and 6 correct. They were more like between 7 and all 9 correct. But even in that range, there was variation, and that variation tracked variation in existing measures of CRT. And adult scores correlated with rational thought. They didn't happen to correlate with normative thinking dispositions. All right, so to summarize, the CRTD does seem to predict rational thinking and normative thinking dispositions in elementary school age children, even independent of their age. And the CRTD seems to be useful for adults as well because it elicits variation that tracks variation in existing measures of cognitive reflection for adults. So one thing we were concerned about early on was whether or not we had created a very culturally specific test, a test that's really only useful for Western children, children growing up in Western cultures, because this relation between reflection and reasoning might be a byproduct of the fact that Western culture emphasizes analytic thought. And not all cultures do that. So, for instance, in Eastern cultures, there's more of an emphasis on holistic reasoning, where individuals are more likely to attend to context, continuity, and similarity, rather than breaking problems into discrete parts. So we thought maybe cognitive reflection might emerge later in an Eastern culture, or maybe it would relate to rational thought and normative thinking dispositions in a different way. So we ran a study with children from China in the same age range, and recruited in the same way at public playgrounds. And they were recruited in 4 different regions of China: the north central, southeastern, and west central parts of China. And then a group of Chinese adults were recruited as well. And here are 7 of our items translated into Chinese. We couldn't use all 9 because there were 2 that were not translatable. They didn't resonate with Chinese culture. One was about Santa Claus, and another one used the rhyme "eeny, meeny, miny, mo," which didn't have a Chinese counterpart. So without those 2, these are the 7 remaining. And we found, and C, I, and O at the top stand for correct, incorrect, intuitive, and O is other. And then we have adults and children. So in general, we saw the same response patterns, where the most common answer for the children was the intuitive response, followed by the correct response, and least often were just random other responses. This is the increase in CRTD scores for the Chinese children in comparison to the American children across the relevant age range. And you can see that those slopes look pretty much the same. So we saw that CRTD scores increased similarly across cultures as children got older. You can also see the red line, which corresponds to the Chinese children, is higher than the blue line corresponding to the US children. That is a statistically reliable difference, but I'm hesitant to make much of it because we didn't control for children's socioeconomic backgrounds in our sampling. So there might be other factors at play in that difference. Chinese children's scores on the CRTD correlated with their scores on measures of rational thought, especially the composite measure, as well as measures of the endorsement of normative thinking dispositions. And again, we found that even when we control for age, the Chinese children's CRTD scores explain variance in rational thinking and endorsement of normative thinking dispositions independent of age. We did another analysis where we looked at whether country of origin, China or America, predicts anything in terms of these rational thought and normative thinking dispositions, and we found that it did not. Age was a significant predictor, at least for rational thought, and cognitive reflection scores were a significant predictor. So we didn't see any substantive differences from the Eastern versus Western samples. The adults showed very similar patterns to our American adults. So their scores on the CRTD correlated with Chinese translated measures of the original measures of CRT. And the Chinese adults scores on the CRTD also correlated with their scores on rational thinking and normative disposition composites. All right, so then to summarize, the CRTD predicts rational thought and normative thinking dispositions in China just as it does in the US, which implies that the Chinese preference for holism over analysis, at least at a cultural level, doesn't seem to impact the emergence of cognitive reflection or its relation to rational thought. All right, so now I'm going to move to looking at the relationship between cognitive reflection and measures of thinking that are a little farther removed from the test itself. And I want to administer another pop quiz. Right. So imagine you're standing in a field with a gun, and a bullet is shot horizontally into this large open field from a gun positioned 5 feet above the ground. A second bullet is dropped from a height of 5 feet at the same moment. Which bullet will hit the ground first? So you have some options. The bullet that was shot, does that one hit the ground first? The bullet that was dropped? Or both bullets will hit the ground at the same time? So the correct answer is that both bullets will hit the ground at the same time, because as soon as the bullets are released, either from the gun or from the hand, a single force acts on both bullets, gravity, and it pulls both bullets to the ground at the same rate. Of course, the bullet that was shot will be pulled to the ground much farther away than the bullet that you dropped, but they'll hit the ground at the same time. Most people, however, predict that the bullet that was dropped will hit the ground first, because they assume that the bullet that was shot was imparted a force, which moves it through the air, but also keeps it aloft longer than the bullet that was merely dropped. Such a force does not exist. The force of impetus, and a force that's been internalized by the bullet. And that's what makes this a tricky problem. To access counterintuitive scientific ideas, which you would have to do to answer the last problem correctly, first of all, that requires knowing some relevant science, knowing a little bit of Newtonian mechanics, and also possibly knowing that there's no such thing as an internal force. But it requires more than that. It also requires suppressing a conflicting intuition, because even scientifically literate adults have this immediate intuition that the shot bullet, there's something special and different about it than the drop bullet in terms of its force status. So you have to suppress that intuition in order to provide the correct answer. And we have found in other work that adults' scores on the adult CRT predict their ability to answer a whole variety of counterintuitive scientific questions. The data I'll share with you today was looking at that same issue for children. So does cognitive reflection in children predict their science understanding? Possibly it doesn't, because both of those abilities are emerging in the early childhood years, both cognitive reflection, as you saw with that graph showing an increased CRTD scores with age, but also scientific reasoning. Children are just learning the relevant science. So maybe they're independent before they become integrated. So in this study, we had 152 children who we administered the CRTD, as well as measures of counterintuitive scientific reasoning and mathematical reasoning. For our content domains, one domain we picked was vitalist biology. That means understanding living organisms as taking in energy from the environment and using their internal organs to convert that energy towards the organism's own goals of growth, survival, reproduction, and so forth, as opposed to thinking of living things as just something that moves on its own. So we had two main assessments of your understanding of vitalist biology. One was just deciding whether or not something is alive, and we presented children with animals, plants, natural phenomena, and artifacts. So the correct answer would be to say that all the animals and the plants are alive and everything else is not. But this is a tricky task for young children, because oftentimes they deny that plants are alive, and they say that some non-living things that move on their own, like the sun and cars, are alive. And then we asked about internal organs, the brain, the heart, the lungs, the stomach, and blood, what they're for, what their functions are. And they got extra points if they noted the interrelations among functions. And then for a different content domain, we selected mathematical equivalence, where we gave children problems that had operators on both sides of the equation, like 1 + 5 = blank + 2. And these kinds of problems are notoriously difficult for children because they initially understand the equal sign as a prompt to provide the answer. So if that's your understanding of an equal sign, you would put 6 in that blank, because 1 + 5 = 6. But if you understand the equal sign as meaning that both sides of an equation are the same, have to be the same, then you would put a 4 in the blank. All right. One thing that some of you might have had on your mind as I've been talking about cognitive reflection is how does this relate to executive function? We know a lot about executive function in childhood, and perhaps cognitive reflection is just an alternative measure of executive function. So executive function is typically broken down into three kinds of abilities: inhibitory control, working memory, and cognitive flexibility. So we wanted to demonstrate that cognitive reflection explain children's science understanding even when we control for executive function skills. So we measured inhibitory control using the flanker task, where children saw arrows and they had to indicate the orientation of the arrow in the middle, and sometimes the arrows that flanked the middle arrow pointed in the same direction, and sometimes they pointed in the opposite direction, and they had to inhibit the influence they got from the flanker arrows to make the correct response for the middle arrow. We measured cognitive reflexibility with the dimensional change card sort task, where children saw cards that had a colored shape on them, and sometimes they had to sort the cards by color, sometimes they sorted them by shape, and which sorting they were doing was cued randomly. So when you switched, you had to inhibit the old way of sorting. Then we also measured flexibility in a different way with a verbal fluency task, where we asked children to name as many animals as they could in a minute or as many foods as they could in a minute. And this taps into flexibility because the way people typically perform this task is they recall subcategories. So you can't just recall animals in general, you recall, say, pets, cat, dog, hamster, rabbit. And then when you run out of pets, you have to move to a new subcategory, like zoo animals, lions, tigers, flamingos. And you have to make that switch on your own. So it's a self-directed kind of flexibility. And then finally, we measured working memory with a backwards digit span task, where we gave children multi-digit numbers, and they had to recall those numbers backwards. And if they got 2 correct in a row, we increased the number of digits in the number up to 8 digits total if children got that far. All right, so here's a graph that shows the predictive power of all our measures for predicting children's understanding of vitalist biology. CRTD scores is the top line in the graph, and the farther right means more predictive. So you can see that the dot corresponding to the CRTD scores is farther along than any of the other dots, indicating that cognitive reflection was the strongest predictor of everything we measured, stronger than our various measures of executive function, as well as stronger than measures of rational thought that we also administered and I had talked about previously. When it came to understanding mathematical equivalence, CRTD scores were not the strongest predictor, but I think they were the second strongest predictor overall, so still important. All right, so thus far I showed you that cognitive reflection predicts existing differences in children's understanding of science. But do they also predict children's ability to learn science? If you are a cognitively reflective child, are you more receptive to science instruction? So that's the next study that we pursued, the next question we pursued. In this study, we had 142 children, also in the 5 to 12 age range, and we gave them the CRTD test, along with a measure of science understanding and a tutorial that was intended to increase their science understanding. So in this study, it was a pre-post design, and at pre-test, children verified 96 true or false statements. Half of the statements were about life, like vitalist biology that we just talked about, and half were about matter. And then they got a tutorial that was 7 minutes, video-based, and it was meant to introduce them to a scientific view of life, or a scientific view of matter, and also refute common misconceptions. And we constructed our tutorial from existing materials that have been validated by other researchers. And we administered some attention checks that all children passed, so they were in fact watching our videos. And then finally, that was followed up with a post-test where children received an additional 96 statements, half about life and half about matter. So let me show you what our assessment materials looked like. So we had some control statements that elicited a correct intuitive response. Statements like bricks take up space, which is true, and dreams take up space, which is false, and we expected children to get those right. And then we had counterintuitive statements like air takes up space, which is scientifically correct, but many children say air doesn't take up space because air is nothing. Or rainbows take up space, which is false, because rainbows are just an optical illusion. But many children say they do take up space because they can see them existing out in the sky. Okay, so first, before I connect these data to cognitive reflection, let me just show you how children performed on this science assessment. So the line at the top corresponds to their performance for the intuitive control statements, and we're looking at proportion correct. So as expected, children did very well on the intuitive statements. They answered about 90% correct, both at pre-test and at post-test. And then the line with the open circles corresponds to our counterintuitive statements like air takes up space. And performance for those items is much lower. But you can see that that line is moving up from pre-test to post-test, indicating that our tutorials did in fact work, that children learned either to suppress some of their misconceptions about life and matter, or they learned some new properties of life and matter in our tutorials. All right, so now relating this to cognitive reflection, in this graph we have CRTD scores on the x-axis, and then on the y-axis it's the probability of answering any statement correct. We collapsed across the intuitive and the counterintuitive in this graph. So first let's focus on the pre-test line, which is indicated with the open circles. You can see that at pre-test, children who had higher cognitive reflection scores answered more questions correctly. They verified more of these statements correctly. That just replicates what we had seen previously. Cognitively reflective children have a higher level of science understanding. Now, if you focus your attention on the post-test scores, you see the same thing. At post-test, kids with higher CRTD scores also scored higher at post-test. But the most interesting thing is that the pre-test lines and the post-test lines pull apart as you move from left to right, indicating that children with higher cognitive reflection scores learned more from the tutorials than children with lower scores. So cognitively reflective children do seem to be more predisposed to learn science than less cognitively reflective children. Before moving to the last part of the talk, I just wanted to point out that there's actually been many studies now looking at the relationship between children's cognitive reflection and some other aspect of higher order cognition. And it's been shown that cognitive reflection scores predict children's possibility judgments, their ability to differentiate physically impossible events from events that are merely improbable. These scores predict their permissibility judgments, so their ability to differentiate immoral events from unconventional events. They predict children's ability to read a 2x2 matrix of data to determine whether the data indicate correlation between the two variables used to construct that matrix. These scores predict children's detection of fake news. Their scores predict their ability to monitor their own consistency in how they respond across a battery of items. They predict the extent to which they'll use evidence to complete an inference task, as opposed to relying on just anecdotes. It predicts their arithmetic reasoning, specifically their ability to use the distributive property in solving equations. And it predicts their number sense more generally. When children are given a whole battery of numeric tasks, cognitive reflection ends up being a strong predictor of how well they just understand math. All right, so the last part of the talk is going to look at whether cognitive reflection can be improved. Because if cognitive reflection predicts all these good conceptual outcomes, then if we can improve cognitive reflection, maybe we can also improve learning and reasoning. So there's been some work on this with adults, not a lot, because as I already mentioned, the adult work on cognitive reflection tends to treat it as a predictor rather than an outcome. They're trying to see whether adults high or low in cognitive reflection perform well or not so well on a task. So studies that have looked at cognitive reflection as an outcome variable, they tend to get weak effects when they try to improve it, or very circumscribed, item-specific kinds of effects. So here's one example. This was a study where they gave adults a 5-item version of a cognitive reflection test, so you could potentially get a score of 5 on this task. The dashed line down the center indicates baseline performance, so how well adults did on this task without any kind of intervention. And then on the left-hand side are a variety of interventions they tried. So you can see the bottom 4 interventions did not improve scores beyond baseline. So that was imposing a time delay, making people think before they responded, or trying to induce reasoning in one way or another. They found that incentivizing correct answers with money helped a little bit, and asking people to justify their decisions helped a little bit. They saw most success when they gave them de-biasing training. That is, they pointed out the biases that led to the wrong answer and encouraged subjects to avoid those biases and reason analytically instead. But this kind of training is item-specific because different cognitive reflection items incorporate different kinds of biases. So you're not going to actually see transfer to a different class of cognitive reflection items with a localized debiasing training. We wanted to find some kind of intervention that was more generalized in its effects. So we went back to basics and just thought, what is required to answer a brain teaser correctly? At least 2 things are required. You have to inhibit the intuitive response that pops into your head, and you also have to be disposed to search for an alternative. Just inhibition by itself is not sufficient, because then you would have no answer to provide. You also then need to seek out an alternative answer. So we designed some tutorials that encourage children to stop and consider either of these things. Consider why their gut response might be wrong, and we called that the why not training. Or consider what alternatives might be correct, and we call that the what else training. So let me give you an example item from this tutorial. The tutorial was structured around 6 zoomed-in photographs like this one. So this is a common object, and we asked children to guess what it was. And we gave them 3 options. Are we looking at cinnamon, rope, or wood? So most children picked wood, and we pre-selected our photos on the basis of knowing that they would pick the wrong answer, because it is not in fact wood, it is cinnamon. We were looking at a zoomed-in portion of the top of these sticks of cinnamon. So after children provided their response, and before we revealed the correct response, we encouraged them to generate reasons why their first guess might not be right. So if they said wood, like, why might it not be wood, and in the why not condition? Or we encouraged them to think of reasons why the other options might be right. Okay, why could it be cinnamon, or why could it be rope? All right, so we had a pre-test before we administered the training where we gave children 5 CRTD items as well as some task measuring executive function, inhibition, flexibility, and working memory. We did that because we wanted to see whether or not our tutorial had its effects, whether the effects of the tutorial were specific to cognitive reflection and didn't improve information processing skills across the board. Then we gave them our tutorial, either the why not tutorial or the what else tutorial. And then we followed it up with 5 new CRTD items that were matched for content and the same EF tasks. So let me explain how we matched our pre-test and our post-test CRTD items. Sort of by happenstance, when we created our original CRT, we had 2 items out of the original 9 that involved the same trick. So for instance, the items, what do cows drink, and who makes Christmas presents at the North Pole, those work by, the trick is a semantic associations. Cow's milk, Christmas, Santa. And you have to inhibit the association and realize there's actually a different answer that's correct. Or the next 2 items, they trick kids into doing subtraction when in fact no subtraction is necessary at all. Our original task did have 9 items, so we took our 1 singleton and created an additional version to complete this set of 10, 5 pairs of 2 items. So we took one item that involved that kind of trick for each of our 5 tricks and created 2 subtests. All right, so the children in this study were 222 children from Parks. One thing that's important to note is that we counterbalanced our CRTD assessments in the event that one collection of items ended up being easier than another. So what was the pretest for some kids ended up being the post-test for other kids. All right, so this is the increase in CRTD score as a function of training, whether you got the why not training or the what else training. I was just picking on the adult studies for weak effects. We also found a weak effect. It's a small but reliable effect for both trainings, and there was no difference between the trainings. It looks like the what else training might have been better, but statistically that's not the case. One problem with looking at the data for all the children is that some of the children were performing near ceiling even at pretest, so they weren't going to increase their score. So if we look just at the low scores, that is kids who got 0, 1, or 2 items correct out of 5 at pretest, we see that there's a more robust increase from pretest to post-test. This is not just a regression to the mean, because if you do the same analysis where you take the kids at post-test who only answered 0, 1, or 2 correct and look at their pretest scores, those 2 scores are comparable. So it only works in the direction from pretest to post-test, implying this really is a training effect. When it came to individual items, we saw these effects were pretty evident across a lot of items. So out of our 10 items, we saw effects for 6 of the items, meaning that if you got the item, what do cows drink, at post-test, you were more likely to answer it correctly than if you had gotten that same item at pre-test. In terms of executive function, we saw no improvements in inhibitory control, cognitive flexibility from pre-test to post-test, so our trainings didn't seem to improve those abilities. There was a small but reliable improvement in working memory, however. So in a subsequent analysis, we controlled for improvements in executive function scores from pre-test to post-test and found that our improvements in our cognitive reflection scores still held strong. But in another analysis, we actually found there was some relationship between executive function and cognitive reflection. So children's cognitive reflection scores at post-test were predicted by their executive function scores at pre-test, even when we control for pre-test CRTD scores and age. So what that implies is that cognitive reflection and executive function are distinct competencies. It was only cognitive reflection that was improved by our trainings. Nevertheless, children with higher executive function scores improved more from our trainings. So let me wrap up then. Children's skill at reflecting before responding, that's another way of articulating what cognitive reflection is, predicts many other skills. It predicts rational judgment and decision making, normative thinking dispositions, conceptual understanding of math and science, the propensity to learn science. And we find that this skill can be facilitated by encouraging children to reconsider gut responses or overlooked alternative responses. These data have methodological implications. The CRTD is very easy to administer, but well, first of all, it's a very strong predictor of higher order cognition, typically stronger than executive function in our own studies, but at the same time, it's much faster and much easier to administer than executive function tasks. So we use the NIH toolbox to administer our EF tasks, and doing so requires practice trials and many test trials, and it's also expensive. And you all can use our cognitive reflection items for free. There are some theoretical implications that follow from these data as well. Thinking about your own thinking seems to be a prerequisite for rational judgment and conceptual change. It's not clear why, though. I mean, what is special about cognitive reflection? It's probably a whole conglomeration of skills that has to come together. And so There's active debate in the adult literature about what cognitive reflection is. Here are at least three possibilities. One possibility is that cognitive reflection really is the tendency to stop and think before you respond. I'm not so sure that's it. I actually think it's probably more like this, that what makes cognitive reflection special is that it requires you to draw upon and coordinate a whole range of executive function skills. Because to answer a brain teaser correctly, you have to inhibit the wrong answer, flexibly search for other answers, all while holding this collection of answers and the original problem in working memory. So all of that has to come together in order to get the correct answer. But kind of a deflationary explanation for what's going on too is that maybe it's just about the desire to answer correctly. Some kids might be okay with giving whatever first pops into their heads, and other kids want to make sure they got it right. And so they're more likely to seek out alternative responses because they're uncertain that whether their first answer was correct. And that you see the same kinds of patterns in other tasks. All right, so I'll end with some educational implications. Cognitive reflection is a useful construct to think about in the classroom because cognitively reflective children appear to be better equipped to learn counterintuitive ideas. So if we can facilitate cognitive reflection as a habit of mind through regular encouragement to stop and think before responding, that might improve educational outcomes potentially across the board. All right, so this work was done with funding from the James S. McDonald Foundation. All of it was in collaboration with my former postdoc, Andrew Young, who's now faculty at Northeastern Illinois University. The Chinese study was done mainly by Tia Gong, and then a whole team of undergraduates also collaborated on this research. All right, so thank you. I'll now open up to questions.